So this is a video for the 2020 first quarter Honors Algebra 2 Progress Check Review. When you take this test in Performance Matters, you will have a formula sheet icon available to you where you can click it, and these are the formulas that will be applicable to you for first quarter. You are permitted to use a calculator for this assessment. One will be provided for you on the Performance Matters site. Another icon on the toolbar will be a calculator that you can use, or you can have your own normal general handheld calculator with you when you take the test. Okay, so our first question here is find the inverse of the following functions. I'm going to start with my mappings of the original function. X then turns to x cubed, then goes to x cubed plus 2. So to map my inverse, I start with x. To undo plus 2, I subtract 2. And to undo cube, I cube root the step before. So f inverse of x is the cube root of x minus 2. Now for h, I start with x, then goes to x squared, then becomes 5x squared, then becomes 5x squared plus 3. So the inverse undoes the original backwards. So to undo plus 3, I subtract 3. To undo multiply by 5, I'm going to multiply by 1/5. To undo squared, I'm going to square root. So my final h inverse of x, you have to write your equation as an equation with the inverse symbol, 1/5 x minus 3. Okay, for c, we start with x, then add 2, then square root, then multiply by 3, and then subtract 1. So to undo backwards, I add 1, I multiply by 1/3, I square to undo the square root, and then I subtract 2. So g inverse of x is 1/3 x plus 2, all of that squared, minus 2. All right, for part C, start with x. X was then taken the cube root, then multiply by 2, then add 5. So to undo backwards, to undo add 5, I subtract 5. To undo multiply by 2, I multiply by 1/2. To undo cube root, I'm going to cube this entire quantity. So my k inverse of x equation is 1/2 x minus 5 all cubed. All right, and lastly for e, we start with x, then add 3, then square the quantity. So the inverse, undo the squared is a square root. Undo the add 3 is subtract 3. So m inverse of x is the square root of x minus 3. Number 2, given the equation y equals x plus 2 squared minus 3, complete the table of values. Then we're going to use these values to write the coordinates on the inverse. So I remember that from the original function to the inverse is a reflection over the line y equals x. So first, if I find these coordinates, I can use them to write my inverse coordinates. So I'm going to take -2 and substitute in to my function. So that's 0 squared minus 3, which is negative 3. Substitute in negative 1. That's 1 squared minus 3. So 1 minus 3 is negative 2. When I substitute in 0, that's going to give me 2 squared. So 4 minus 3 is 1. One plus 2 squared, so that's 3 squared minus 3, so 9 minus 3. And then I substitute in the 2. That's 16 minus 3. And I have my 5 coordinates. So to find my inverse coordinates, that reflection over the line y equals x, my x and y coordinates switch locations. So it becomes negative 3, negative 2, negative 2, negative 1, 1, 0, 6, oops, 6, 1, and 13, 2. All right, here's a similar problem, but now I have x minus 4 cubed plus 1. I'm going to do all my work over here. So we substitute in negative 2. That's negative 6 cubed plus 1. You are allowed to use your calculator. So if you choose to use your calculator for a quantity like negative 6 cubed, this parenthesis is very important. That's negative 216 plus 1, so we get negative 215. So now we have negative 5 cubed plus 1, negative 125 plus 1. And now 0. And now 1. And last but not least, 2. That's, it's a cubed. So it's negative 8 plus 1 and negative 7. So for my inverse coordinates, same as the problem before, reflection over the line y equals x makes my y's become x's and my x's become y's. Solve. Indicate if there is no real solution. Okay. So I'm going to use my inverse operations to solve. Subtract 2 to both sides. Square. I get x is 81. And anytime you start with a square root, you have to check your answer to make sure it's not extraneous. And that equals 11, so 81 is my answer. For B, I'm going to divide by 3. Square both sides, I get x is 16. Again, it's a square root, so I have to check. And that's 12, that works. Now for C, I have a cube root, oops. And when I cube both sides, x is 27, and I don't have to check my cube root solving because there will be no extraneous answers since the domain is all real numbers. So that's one last step for a cube root problem. can cube both sides here. Subtract 3. I get x is 5. Again, it's the cube root. I don't have to check my answer. Now for E, I see that I have this square root equaling a negative output. I can know right away this is no real solution. There is no number I can substitute in for x that would make this statement a true equation. Let's say I didn't realize that, and I square both sides. And I get x equals 13. I have to check because I started with the square root. So will the square root of 13 minus 4, the square root of 9, that's positive 3. That is not negative 3. So 13 is not an answer. There is no real solution to part E. And then for F, just divide both sides by negative 5. Oh, I got a square root equaling a negative. That means there's going to be no real solution. If you wanted to solve all the way and then check just to be sure, if my check I go back to the original, that's negative 5. Let me make that look a little nicer. Whoop. Undo. Okay, checking into the original. Negative 5, square root of 38 minus 2. That's negative 5 times the square root of 36, which is negative 5 times 6, which is negative 30. That is not positive 30. That does not check. 38 is not an answer. There's no real solution to part F. Oh, now we've got graphing. Make this a little smaller. There we go. I'm going to graph by my transformations. So I know the parent function for the square root of x. The parent function has these first coordinates as their values. So 0, 0, 1, 1, 4, 2, and 9, 3. And then if I think of the transformations on this graph, we have reflect over the x-axis, left 1, and down 3. So I'm going to take all 4 of these points through all of these reflections. 0, 0 doesn't reflect. So I'm going to go left 1 and then down 3. That's my endpoint at negative 1, negative 3. Now this point, reflect, left 1, down 3, reflect, left 1, down 3, reflect, left 1, down 3. Let me erase those points. So there is my graph, kind of squiggly, but you get the idea. Okay, so I have to answer domain and range for this graph. Domain is the x values, and I have every x greater than or equal to negative 1. And the y's are decreasing. They're below that endpoint, so it's every y less than or equal to negative 3. All right, let's do G. Let's start with these same parent function points because it's a square root. And this transformation is right 3 and up 2. So I'm going to take every point, right 3 and up 2. Right 3 and up 2. I did a better job graphing that one. It's not as squiggly. Whoops. Woo. That's better. Okay, so the endpoint is now at 3, 2. All my x's go greater than 3, and all the y's are greater than or equal to 2. Ms. Menifee wants to determine the average rate of change. Anytime I see the word average rate of change, and I think slope. This is back to Algebra 1, slope. Between the coordinates of the function y equals 5 root x. Write your answer as a reduced fraction. Okay, well I have x's, I need y values. So 0 comma something, 4 comma something. So when I substitute 0 into my equation, Miss Menifee will get 0. When she substitutes in 4, that's 5 times 2, 10. So here we go for our slope, x1, y1, x2, y2. So y2 minus y1 over x2 minus x1. Reduce your fraction. Miss Menifee has her answer. All right, so let's try from 1 to 25. So it's 1 comma something, 25 comma something. When I substitute 1 into my equation, that's 5 times 1. When I substitute in 25, that's 5 times 5, which is 25. Okay, x1, y1, x2, y2. So my slope is 25 minus 5 over 25 minus 1. Both of these are even numbers. Let's divide by 2. Up, still even numbers. Divide by 2 again, I get 5/6. All right, now Miss Salisbury wants to determine the average rate of change. Ooh, and she has a different function, -2 cube root of x. So I'm going to find my coordinates 0 and 8. So 0 comma something, 8 comma something. I need these y values. So -2 cube root of 0. Well, -2 times 0 is 0. -2 cube root of 8 is -2 times 2, so that's -4. All right. x1, y1, x2, y2. Our slope is -4 minus 0 over 8 minus 0. Reduce that fraction, and we have a -1/2 slope, or average rate of change. All right, 2 new coordinates, 1 comma some y value, 27 comma some y value. Substituting in to find those y values, that's -2. -2 times 3, that's -6. x1, y1, x2, y2. So we've got -6 minus -2, 27 minus 1. Reduce. We have -2 over 13. Okay, rewrite the expression in radical form. So when I have these rational exponents, I know that this denominator is the index on my radical. So when I have 2/5, I'm still going to have the 5th root. So it's either the 5th root of x all squared, or you could have it as the 5th root of x squared. 7/5, so that is 5th root again, x to the 7th, or the 5th root of x all to the 7th. Now we're going to go the other way. Take our radical and let's rewrite as a rational exponent. So the 6th root becomes a 1/6 exponent. A 6th root again, but now I have that power of 5. So my 5 is my numerator and the 6 is my denominator. Cube root now, the denominator is the 3rd and the numerator is squared. Simplify completely. Okay, we're going to use our laws of exponents here. When you multiply and your bases are the same, you can add exponents. So then this 4 plus this 1 makes a 5. So we have x to the 5th, y to the 5th. When you have a monomial to a power, I'm going to first do the power to the power. So that means 2 times 4 is x to the 8th. 3 times 4 is y to the 12th. And then when you divide, you can subtract your exponents. So this denominator, they each have an exponent of 1. So 8 minus 1 is 7, and 12 minus 1 is 11. I'm going to start C the same way with that power to a power. So we get x to the negative 8th, y to the negative 12th. And now when I subtract, negative 8 minus 10 is negative 2. Negative 12 minus 6, negative 18. And then we don't want negative exponents in our answer. Since we have a denominator of 1, the numerator, I ran out of room, is going to stay that coefficient of 1 that's out here. We don't usually see it. And then the negative exponent says move to the other side of the fraction and make your exponent positive. Nancy decides to invest $1,000 in a bank account after she graduates from high school so that she can have money after graduating 4 years later. The account she invested is 8%. So don't forget about your formula sheet. Your formula sheet will have this equation. I'm actually going to go screenshot that and put that here. And ta-da, here it is. Okay. So they are telling us in part A, write an equation that represents the total amount of money if her interest is compounded annually. So that's an N of 1. So she deposits $1,000. 1 plus, we have to write our 8% as a decimal. 1, and then T. How much money will she have after 4 years? So I'm going to substitute in 4 to T. This is where you need your calculator on the test. Oops, I don't want that. So we got 1,000. 1 plus 0.08 to the 4th. And she will have $1,360.49. You have to round appropriately to the nearest hundredth. Okay, let's see what this next one is. Compounded monthly, so that's an N of 12. So same interest, but now over an N of 12 to the 12T. How much money will she have compounded monthly after 4 years? Let's see. Now, if you have an older type of calculator like mine, where it does not put the box in the exponent, doesn't have that little dash box, you need these parentheses around your 12 times 4, unless you just type 48. But if you don't want to do that multiplication first, you have to put those parentheses there. And that would be $1,375.67. If you have the newer kind of calculator with the math print, the way you type this, your exponent actually puts the exponent in that little exponent location. The calculator is grouping it based on putting it up there in that little box, and you get that same answer. Since I've been using one of these since the 90s, I like the classic print. I'm going to keep mine in classic. Okay, write an equation compounding quarterly. So that's an N of 4. Same interest rate, 8%, but now it's 4 time periods. How much money will she have after 4 years? All right, let's see. $1,372.79. You are studying the population growth of fruit flies. Your teacher tells you that the fruit fly population grows by a factor of 4 each week. What growth factor or multiplier could you use to determine the growth from one day to the next? Okay, so the original multiplier is 4. How many days are in a week? That's 7. So I'm going to use the power of 1/7 to change that multiplier. If it helps you to lay out a table, like when we originally did this in our exponential unit, we started that very first day with a table and a little experiment between, I think it was Travis and Miriam. If you like a table, you can do that. I'm just going to think about changing my unit from weeks to how many days. Okay, the number of fruit flies in experiment now triples every 30 minutes. If the fruit flies initially is 500, now we're going to write a function that models the number of fruit flies after t minutes. Okay, so f of t is the initial value, the multiplier, but now instead of just being to the t, because it's at every 30 minutes, I'm going to have t over 30. And now for 14, more fruit flies. Now we're going to double every 15 minutes. We still start with 500 flies. And now it's still a function after t minutes. So we have f of t, initial value, multiplier, now it's double. But instead of just in minutes, it's every 15 minutes, so it's t over 15 as your exponent. It's similar to the way we changed this multiplier here, but number 12, that wasn't asking for an equation, that was just asking for the new multiplier. Since 13 and 14 are actually asking for the equation, if I just wanted the new multiplier, this is what I would have. But now we're using that base in our exponential setup of a times b to the x. So this x, or the t, is multiplied by that 1/15. All right, graph both functions, then complete the questions below. Okay. Got this exponential. I'm going to use -1, 0, and 1. I know this is a growth since the base is more than 1 and my exponent is positive. So when I substitute in -1, get some room here. That's going to be 3 times 2 to the -1, which is 3 times 1/2. So that's 3/2. When I substitute in 0, anything to the 0 is 1, so that's 3 times 1. And then 2 to the first, so that just gives me 6. All right, -1, 1.5, 0, 3, 1, 6. And I know I have this dash line. I have my horizontal asymptote here. The horizontal for an exponential. Here's my growth. It's continuous. Put arrows on the ends. And now let's see what properties we need. Just gonna take a picture so I can bring this down to where my properties are. Oop. Okay. Now I can talk about it all on the same screen. So a domain is my x values. I can continue all the way left. I can continue all the way right. So domain is x is all reals. My range, I only have values higher than my asymptote. I get really, really close, teeny, teeny, teeny decimals, and then go up in the y. So y is greater than 0. That's kind of crooked. My horizontal asymptote is the line y equals 0. If you're stuck on whether it's x or y equals, think about any coordinate along this line. All the y's are zeros. All right, and then is this graph increasing or decreasing? As I read my graph left to right, if I'm walking, all the y values are going up. This graph is increasing. All right. Now, g of x has that base of 1/4, so I know this is going to be a decay graph since the base is between 0 and 1, and my exponent is positive. Calculate some coordinates again. So I have that 1/4 and the -1, which is 2 times 4, so I get 8. 0 is going to give me 2 because 1/4 to the 0 is 1. And then 1, that's going to be 1/2. All right, -1, 8, 0, 2, 1, 1/2. Approach that horizontal asymptote again. I'm going to make sure I can do it in a color you see it. There we go. So there's my horizontal asymptote. Let me do the same thing where I can see my properties at the same time. I don't know why when I do that, it makes it so humongous. All right, here we go. Now my decay graph. Domain is still all real numbers. That is true for every exponential. Every exponential graph will have a domain of all real numbers. The range is y is greater than 0 again. Still the same horizontal asymptote. But this graph now is decreasing. Okay, congratulations, you made it to the end of the progress check review. Before the test, you should be able to do all these problems confidently, independently, without help, in an efficient way. So you can print and do as many of these review sheets as possible. until you can answer all these questions confidently and independently.